Well, before we move to variable substitution, I'd like to give you another way of looking at this integral right here. Instead of saying that we are getting the areas at different values of y and then creating volumes and adding those volumes to get the final overall volume, we can think of this in a different way. We have this integration as the integration from x1 to x2 and also from y1 to y2 of f of x and y, which is the height, then dx dy. We can think of this as having a very small square area, maybe like that, having an area of dx multiplied by dy. So we are partitioning our base here into many small areas. Every one of those areas is a square area having an area dA equal to dx dy. So this is equal to here f of x and y multiplied by some very small area dA. Then for every dA of those, you are multiplying this small area by this height, by f of x and y, and so getting a very small volume. And then if you add all of those volumes together, you will get the complete volume under this function you have. So for example, you can have this very small volume. So here I intersect here, here I intersect, let's say here, this right here. So I think this should be somewhere here. So I can have this. Then I can have this, and also I can have this and this. So this is my very, very small volume I have. And for every square of those, I'll have another small cube or rectangular parallelepiped like that. And if I add all of those volumes together, I'll get the complete overall volume. Okay, so this is a nice different way of looking at the same integral. Now I want to give you one more note. What will we be calculating if we choose this function right here to be exactly equal to 1? So what is this? Integral from x1 to x2. Here, integral from y1 to y2 of 1 multiplied by dx dy. Now we have a function that has a constant height of 1. So we have x here, we have again y here, then we have some specific area. So let's say this and this and then this and this. So here this is x1. Let's make it white. So this is x1, this is x2. Now this is y1 and this is y2 and this is the y-axis, this is the x-axis, and we have above this area, this yellow area, we have a function that has a height of 1, and we are calculating the volume under this function. But the volume under this function is really equal to the area of this base, because the volume is equal to the area multiplied by the height, and since the height is always equal to 1, then the volume under the curve is really equal to the area of the base. This means that if you want to calculate some area in 2D, so here I have this x-axis in 2D and this y-axis here, and if you want to calculate some area, maybe some area like that, you could use double integration for your calculation. So you could use some integral here of dA, and every dA is a very small area, a very small, let's say maybe rectangular area like that, or like that, and then add all of those very small areas until you get the final area. So this is equal to the integration of 1 multiplied by dx and dy, and you should choose your limits of integrations properly. In general, the limits of integration right here need not be constants. For example, the limit for x might be some function of y here, and some other function of y here, because anyway, after you perform this integration, you will get a function of y. We will actually see an example for this if this is not clear. Now, the limits for the outer integral must be constants, because this area will be just a number, right? So here I'll have some constants for y. So starting from y equal to something, y node, up to y equal to, let's say, y1. So let's take a simple example for this. Suppose we have our triangle. So maybe I have something like that, this triangle, and I want the area from here to here. So suppose this is, let's say, 6, and I want the area from 3 to 6, and let's say that this function is f of x is equal to x. Now I know that I can get this area by a single integration. So this integration can be written as the integration from x is equal to 3 up to x is equal to 6 of x dx. And so this area is really equal to x squared over 2 from 3 to 6. So this area is really equal to 1/2 here multiplied by 6 squared minus 3 squared. So this is equal to 1/2. This is 36 minus 9. This is 3 squared. This is 3 squared, which is 9. So this is 27 over 2. Now I want to calculate this same area using double integration. So let's get this with us. I need some double integration here. My function is 1 because I'm calculating an area, not a volume. And here I have dx dy. Now I have to decide my limits of integration. So what should I do? I have two options. Either I will create horizontal areas like those. So I will calculate the areas at every height as a function of y and then add all of those areas together. So this will be the first option. Or I will create vertical areas like that as a function of x and then add all of those areas together. I prefer the second option because all of those vertical areas have the same limits everywhere. For every possible x, the starting of this vertical area is at 0 and the end of the vertical area is at this function f of x is equal to x. While if I used horizontal strips, I would need to partition my area into two areas, this square right here and then this triangle right here, because for this square the limits for x start from 3 to 6 always, while for this triangle the limits for x start from y up to 6. So I'll have two different integrations. Any one of those will work, but I prefer those vertical strips because I will only have one integration. Now, since this is y and this is x, then for those vertical strips, I will perform the integration in the y direction first and then perform the integration in the x direction. Now, for this y starts at 0 and ends at x. So this is a function of x. Here I have 1. After that, I will have created all of those areas, so I need to integrate from x is equal to 3 up to x is equal to 6, and if I perform this integration, I'll find that this is equal to y from 0 to x, and here I have the integration from 3 to 6 of dx. Now this is equal to the integration from 3 to 6 of x minus 0, which is x, multiplied by dx. Remember, this is actually the same integration right here. This is this, so this will give me the same result of 27 over 2, which is the same area. So we got the same area using two different approaches, which is quite nice. Of course, this number right here is correct because we can calculate the area of this square to be 9 plus the area of this triangle to be equal to 3 over 2 multiplied by 3, which is 9 over 2. So I have 9, which is 18 over 2 plus 9 over 2, and this is really equal to 27 over